There we go. I'm all set here. Hi everybody, welcome back to 161. Let me turn this down here. Yeah, Subnautica is one of those games that I've been told, like, hey, you like those building games like Satisfactory? You should play this. And then I watched somebody play it and they immediately got eaten by a shark. And I was like, nope, that's not a game I want to play. Not a game I want to have anything to do with. Maya says hi. So we're going to talk about acids today. Maya's going to talk about whatever she talks about. Say hi. Maya. Maya just wants to acknowledge. She wants acknowledgement that she exists. Hi, Maya. Go sit on your chair. I touched her tail. Now she thinks I'm going to pay attention to her. Things on the agenda for today at the bottom of the screen. So, quiz number 3. It's not quiz number 3, sorry. It's quiz chapter 3. And lab worksheet 4 are due tonight. Make sure you get those in by the deadline. Tomorrow's the last call for those 2 assignments. Yeah. Really not much to say about that. There's only one more quiz left, and it's chapter 4's quiz. There isn't a quiz on chapter 5. And hopefully we'll get through chapter 4 either on Wednesday or Tuesday next week. I guess it'd be Monday next week because we have a review. We need to finish talking about acids. Oops. I bonked the cat with my foot. We were naming compounds last week. We named ionic compounds. We named covalent compounds. But we did not name acids, so we're going to do that. 1 hour exam 2 and final. Check the syllabus. Those dates are in the syllabus. I don't know them off the top of my head, though. So, to name an acid... Sorry, we had to spray bottle the cat because she is just not leaving me alone. To name an acid, first you need to know the formula of an acid, and that requires us to know what exactly an acid is. So, acids contain this in them, H+. There's going to be enough H+ to neutralize whatever the charge is on your anion. So if you pair it with phosphate, the charge on phosphate is 3-. I'm going to need 3 H+ to balance out the charge, and then that will be my formula. So if you know the polyatomic ions, the naming acids is really easy, and writing their formulas is really easy because it's all the information is just right there. You just balance the charges. But if you don't know the polyatomic ions, then you got to go look them up, and that eats up time, and that's a valuable resource. So just be mindful of that. Now, depending on the acid you are looking at, some cases the state of the acid matters when you name it. This very rarely comes up because, for the most part, the acids that we deal with are aqueous. And so we just use the aqueous rules and we're fine. Your text does mention, though, that in the gaseous state the names are different. And so I present both of the names here for binary acids, just in case like you run into that and you're like, oh, why is it hydrogen chloride? Isn't it hydrochloric acid? Well, it's hydrogen chloride in the gas state. So first we're going to write the algorithm for gaseous acids. So if your acid is a gas, this is the algorithm that you use. You're going to write the word hydrogen. Then you're going to write a space. Then you're going to write the name of the anion with "ide" after it. And so we saw all the ides on Wednesday last week when we were discussing ionic compounds. So chlorine and hydrogen put together as a gaseous acid would be hydrogen chloride. The reason for this is because in the gas state, acids don't really dissociate as acids. They just act like molecular compounds. They just sort of bonk around and do all sorts of stuff. But the second they enter water, that's when the acid effect happens. Now, when you have them in water, we change the naming scheme a little bit. So here we have hydro blank acid. So this stuff that's in black text here, you're going to use that for every name, as long as you fall into these categories. The blue stuff is what you're substituting out. Now, what are the anion stems if you looked through all of the ides, so for example, if I wrote chloride here, the stem is whatever the ide is without the ide. So the stem for chloride would be chlor, if I just get rid of the ide. So I would put this into this spot right here, and we would get hydrochloric acid. And that's where the name comes from. Now, there are some exceptions to these stems. For example, if I have sulfide and I put sulf in there, it doesn't sound right. So what chemists do is they change it to sulfur. And they do the same thing for phosphor. So phosphide becomes phosphor. Other than that, all the stems just drop ide. And that would be how you name these. Now, these are for binary acids, so you're not going to see things like H2SO4 as a gas named like a gas. Those are just named sulfuric acid for some reason. But if you have a binary acid, check the state first of all, and then apply the correct rule. So I have some examples on the next slide. The last thing that I do want to mention, though, is that hydrocyanic acid follows these rules. And the reason for that is because cyanide ends in ide. So it acts like all the other things that end with ide, which is chloride, bromide, fluoride, sulfide, etc. Really, what your textbook should say is just, oh, your acid ends in ide, follow these rules. Oh, your acid ends in something else, follow these rules. But it doesn't for some reason. So I'm trying to match with the text. So here's some examples here. So these are gaseous, so we're going to name them with the hydrogen space, and then whatever the element is with ide. So that'd be bromide in this case. And fluoride in that case. And so this is because they're a gas. Now, if they're aqueous instead, we do the hydro blankic acid. So this would be bromic acid. And HF would be hydrofluoric acid. Yeah, so it would be hydrophosphoric acid if you had this. Now, interestingly, that doesn't exist, H3P. And also interestingly, this does exist, or at least theoretically. And you might be like, what the heck? Oh, you just move the P to the front. Those are the same thing. And the reason for that is this is actually a base, so we don't name it using the acid rules. So, yeah, you hit some kind of weird stuff here. It's kind of like H3N doesn't exist because NH3 exists, and NH3 is a base. So we're not going to name H3N following the acid rules because it's a base. But if H3P was a thing, that would be its name. It would be hydrophosphoric acid, minus the hyphen. So yeah, no hyphen between these two. I'm not going to give you theoretical compounds. So, like, I'm not going to give you H3P or H3N. Because if you type H3N, you're going to get ammonia, and you'll type in ammonia and get marked wrong. And that's sort of fair. That's, like, wait a second. Isn't this ammonia? Yeah, it totally is. Excuse me. Now, if you have a polyatomic ion in your acid, instead of just one anion, then what you 99% of the time have is what's called an oxyacid. Oxyacids contain oxygen in the polyatomic ion, and they have varying different names that affect how we treat our acid as a result. And what I mean is that the names tend to end in one of these prefixes. So, for example, this polyatomic ion ends in 8, whereas this polyatomic ion ends in ite. And all of the polyatomic ions that we are dealing with end in 8 or ite. Nearly all of them, anyway. So we can make acids out of these compounds by following some simple rules. And those rules are the following. If your acid ends in 8, then you're going to strip off the 8 and replace it with ic acid. And if your polyatomic ion ends in ite, you do the same thing, but you strip off ite and replace it with us acid. HSO4 is missing some H's in there. And also, that's not a binary ionic compound, or binary acid, so it would not follow the previous rules. HSO4 would follow these oxyacids rules. More specifically, H2SO4. So for naming oxyacids, it's actually quite simple. You're just going to take off the 8 or the ite and replace it with the correct suffix. We do not have oat. This is not Raffi. We do not opals and bononos here. We ate and we ite. That's it. Alright. So, I make the Raffi joke, but like 95% of my students probably have no idea who the heck Raffi is. Like, he's a folk singer from... He's older than me, but when I grew up, I grew up in a house that had friends that brought over Raffi. I don't know. But he did the I like to eat apples and bananas song. And then you just go through all the vowel sounds. Alright. Give the name for whatever the hell this is. So first of all, we need to figure out what this ion is. So remember that all the H's are always going to be H+, because they're acids. And that you have one H+ for every charge on the ion. So you can deduce that this must be the ion. And then you can go look it up. Or perhaps you have it memorized and you're like, hey, that's acetate. Now, acetate ends in 8, so what we're going to do is we're going to get rid of the 8, and we're going to put ic acid on there. And so we should get acetic acid. Or, how we would pronounce it, acetic acid. And it is vinegar, yes, very good. Acetic acid is great on fish. And the reason that we like vinegar on fish is because acids will neutralize the fishy taste. Because fishy taste is actually from a molecule that is basic. And if you neutralize it with added acid, the fishy taste goes away. This is also why you put lemon on fish, because the citric acid does the same thing too. Hooray food. Alright, what about this one? We can do the same process here. So I have this, and I can go look that up, and this is nitrite. Be careful, nitrite has NO2 with a minus charge. Nitrate is NO3 with a minus charge. So it ends in ite. We're going to get rid of that and replace it with us acid. So us acid. There you go. And then I think the next examples I have are, remember that if we have sulf or phos, these are our stems that we might get from something like sulfate or phos. That should be an O. Let me just erase that. I don't know, something like that. If you get rid of that, for some reason what we do is we add extra letters. I think it's just to make it sound better, but I'm not the person who made up these rules, so make sure you do that on Canvas. So if I give you these two things, and I say name this, don't name this sulfus acid. Make sure to add the UR so it's sulfurous acid. So we got two H pluses. We got this, which is sulfite. So this would be sulfurous acid. And then for the phosphate one over there, we got that. That's phosphate. We're going to get rid of the 8. It's phosphoric acid. Now, a lot of these acid names you've probably heard before, so this is just how we're getting to them. So, like, I think anybody who has any interest in automobile racing has probably heard of nitrous. I believe nitrous is NO2. Alright, I'm going to put these acids on the board here. What I want you to do is I want you to give a name to these acids at the top, and then write the formula of the acids at the bottom. Note that the last one is not periodic acid. That is per iodic acid. A lot of people look at that and they're like, what the hell? But in order to do this, you do need your polyatomic ions list, and that's at the start of Chapter 6. So, if you have the slides for Chapter 6, they're on the Modules tab in Canvas. Go download those real quick. Have the list of polyatomic ions handy somewhere so that you can use it whenever you need it. And then you name these acids. So, I'm going to give you about 5 minutes to do this while I go and get another seltzer water because I drank all mine. And we'll go over the answers in a little bit. One more minute, we'll go over the answers. All right, let's go over the answers here. So, a lot of this comes down to identifying the ion and then finding its name. Oops, I forgot the per here. And then just replacing the end with what it's supposed to be. So, the first one would be perchloric acid. The second one here, where I, oops, wrong end of the pen. This is hypobromite. We'll just get rid of the ite, and then we'll stick us acid on the end. Hypobrom-us acid. Down here, there's the dichromate ion. We'll get rid of the 8. We'll replace it with ic acid. And then this is just the weird exception. Which I throw in there. It's the one polyatomic that follows a different rule for naming the acid. Just because it ends in ide. Cyanide, anyway, ends in ide. This one follows the rule we've been doing so far. PO3, 3 minus. This is phosphite. We get rid of the ite, and this becomes phosphorus acid. Now, keep in mind that the difference between phosphorus and phosphorus is this O here. And a lot of people omit that O or forget that O. If you're typing it into Canvas, that O is important. Be alert about that. To go backwards, here's what I do. So ic means replace with 8. So I'm going to get rid of this part. So there's sulfate. I can then go look up what sulfate is, and I can then add enough H's to balance the charge. Over here for nitric acid, I can get rid of the ic and say, oh, okay, that's nitrate. We'll write down what that is. Then I'll add enough H's to fill it in. For chromic acid, get rid of the ic. That becomes 8. Then we gotta go look up what chromate is. And then you can make the acid. I wrote the wrong letter. Sorry, there is a car right outside my window. I have no idea if that was going through the mic. All right, here I have us on the end. Us becomes ite, so I need hypochlorite. That's this. So my formula becomes HClO. And then finally, for periodic acid, which is actually periodic acid, it becomes 8, so periodate. Periodate is that, which becomes this. All right, that's naming acids. So remember that for binary acids, which is 2 elements, there could be the gaseous or aqueous version. For all the other acids, just one way to name it, no matter how you find it. We're going to find only aqueous acids in the laboratory because we don't have a sealed cylinder of HCl. Like, that's just dangerous and corrosive to store, so we don't do that. But yeah. All right. Let me know if you have any questions about that. Periodic acid and hydrogen peroxide are not the same thing. Hydrogen peroxide is H2O2. Hydrogen peroxide is technically not an acid. All right, we're going to start drawing Lewis symbols finally. Yay! Excuse me, I need more water. So we're going to start drawing the structures of molecules today using a scheme devised by this chemist here. So this is G.N. Lewis. And what G.N. Lewis did was he did a lot of work with ionic compounds and drew these sort of cubes in his notebook. And his thought was, okay, my valence electrons maybe can occupy the corners of a cube, kind of like the vertices. That's what they're called, I guess. And if I can get to 8, then I get a stable compound. So, for example, sodium here provides this 1 electron, and chlorine here provides the other 7. And you might remember that sodium has 1 valence electron, and chlorine has 7 valence electrons. And then if you could fill all the corners of the cube, then you would get a stable result. And so Lewis predicted, oh, okay, if I can get NaCl by just moving electrons around, then this must be the formula that occurs. And it totally is the compound that we observe. He's just trying to devise a model that represents this. And so what we do is we have incorporated his Lewis structure, not with this cube standard, but with a bunch of dots around stuff, and we've called them Lewis symbols in his honor. And the Lewis symbol might be the most useful thing that we will cover in this class in terms of what do molecules look like. Because not only can we draw them with the correct geometry, and we're going to study geometry like tomorrow, but in organic chemistry and other classes where structure matters, so in biology, the structure is everything in your molecule. Enzymes work or don't work based on the structure. Knowing what the Lewis structure looks like of your molecule will help us elucidate that whole entire process. So drawing the Lewis symbol of any element is very simple. We're going to start with elements and we're going to do entire molecules. But to do it for a symbol, it's a 2-step process. First, draw the chemical symbol of the element, whatever it is off the periodic table, just write it on your paper. And then step 2, draw a dot on each side of the element. There are 4 sides, top, bottom, left, and right. 1 dot per valence electron until you get up to 8. This could not be easier. Now we're only going to be drawing in valence electrons. So for sodium, I have written its electron configuration. And you can see, oh, I have 1 valence electron. So let's follow that 2-step process. 1, write the symbol. There you go. 2, draw a dot for each electron. There, it's done. Easiest thing ever, right? Now, how the hell do I test you on this? I have to have you type things in about your answer. So I'd be like, how many unpaired electrons are there? Well, there's 1. Now, this is the easiest thing you're going to do in this class, but it's also one of the most important, because from here, we're going to do so many different things. Let's do an example for oxygen. So first, let's look at oxygen's electron configuration so we can count its valence electrons. There it is. So you can see I have 6 valence electrons in n equals 2. I'm going to draw 6 dots around the atomic symbol for O. There you go. And then we'll put the dots in. Now, if I have 6 dots, you might think, well, I'll just do this, right? But electrons repel from each other. And if there's this whole empty space available, someone's going to want to occupy that. Since electrons don't want to be next to each other unless they have to, we need to spread the electrons out as much as we can over these 4 orientations. And if you've guessed, well, there's 4 directions I can put electrons, and there are, in the n equals 2 orbital, there are 4 orbitals. N equals 2 level, I should say. There's 2s and 2p times 3 for 4. Yeah, that's where we're going with this. Is one of these orientations is S and the other ones are P, and they're all equivalent anyway. And then in chapter 5, we're going to change it up a little bit. So I would get something like this when I put my 6 dots down. Now, which direction you put the 6 dot doesn't totally matter. So if I do something like this is okay. Because I have 2 unpaireds in oxygen, and as long as I have 2 unpaired, that's fine. So they can go in any orientation you want to. But again, something like this would be wrong because I have an empty space here. So make sure you're numbering 1 on each side, and then start pairing. All right. I'm going to have you draw the Lewis symbols for each of these elements and the ion shown below. Now remember, if I have an ion, I modify the number of valence electrons here. And remember, we don't really need to deal with electron configurations to figure out the number of valence electrons because you could just use the group number, right? In fact, I think I say that on the next slide is that, hey, we'll just look at the group number. So specifically the ones digit. So carbon being in column 14, the ones digit is 4, so it has 4 valence electrons. So if you don't want to write out the electron configuration every time, because what we're dealing with is on the next slide or something like that, that's fine. So draw the Lewis symbol. I'm going to give you like 2 or 3 minutes to do that. I'm going to type the answer to this per question in the chat, and we'll go over the answers in a bit. 1 or 2 more minutes. All right, let's go over the answers here. So I'm going to write out the electron configurations just to show what these are. Oops, not 2p4. So here's carbon. There are 4 valence electrons, so we would draw C with 4 dots around it, 1 on each side. For lithium, there's only 1 valence electron, so we draw 1 valence electron, and there it is. No, be careful with lithium especially, that you don't accidentally interpret that as a dot. So most people just make out like a really big stupid dot for lithium when you have to draw its Lewis structure. All right, for sulfur, we've got 3s2, 3p4? Yeah. So sulfur would look like this. There are 6 valence electrons. 1, 2, 3, 4, 5, 6. I just go around and around and around, and wherever I end up is where I end up. For chlorine, same thing, but 3s2, 3p5 instead. So 1, 2, 3, 4, 5, 6, 7. Let me get rid of all this here. For aluminum, I have argon 3s2, 3p1. So that's 3 valence electrons. So we'll do 1, 2, 3. There you go. Now, for boron with a plus charge, first I'll write out boron's electron configuration. And then I'll make it have a positive here, so we're going to get rid of this one. So now there's only 2 electrons. So I would just draw those 2 electrons. Now, because it's an ion, we do have to include its charge somewhere. And the way to do that is square brackets and the charge at the top right. So this would be the right way to do B with a positive. Here's bromine. We only care about the valence layer, so we're going to have 7 valence electrons, but it's got this minus charge on it. So now it has 8 valence electrons, and so we'll draw that way. So 1, 2, 3, 4, 5, 6, 7, 8. So there's bromide. And then by the same extension, xenon here is a noble gas, so it's going to have a full S and P subshell. And when I write this out, krypton 5s2, 4d10. There's my full S&P subshell. So I'm going to draw 1 dot for each of those 8 valence electrons. So now that we've gotten to this point, we can use electron configurations to figure out how many valence electrons there are. We can then draw that many dots, and we can use that to model our bonding, which is what we're going to be doing in this section. But we're going to be doing that when we come back from the break. So let me put the, let's put this on the screen here. I need to clear this, actually, because I was using it for something else. All right, I'm going to hit start on the timer here. And I'll see you in 10 minutes. Alright, we are back. Yeah, I really like the soundtrack to Axiom Verge. It's really good. Also, it's a really good game. Like, if you like Metroid games, go play it. The second one's coming out. I can't wait for that. Alright, so what we're gonna do now is we're gonna show how we can get to the answers for our ionic compounds formulas that we calculated in previous sections where we were like, oh, we want to make sure everything has a noble gas configuration. But now what we're going to do, and we've already done this slide, so we don't need to actually watch Lonnie's lab again here, but we're going to show our electron transfer instead of showing that I'm moving one electron from the sodium's 3s orbital into chlorine's 3p orbital. I'm going to just show that graphically. Dude, there you go. And so what ends up happening here is that when I do electron transfer, I can either consider it from the orbital approach, which is write out all the electron configurations, and then try and get everything to match a noble gas. Or we can just say, well, all noble gases have 8 valence electrons, so I'm just going to try and make pictures that have 8 dots around them. Remembering that if I strip away all of the valence electrons, the next layer down becomes the full S&P subshell. So getting to 0 also counts as 8. Why are there so many cats in here? No. Leave. Oh my goodness. They're both meowing at me. I'm like, no, that's not going to work. All right, so our goal becomes what was originally, oh, I'm just going to make everything have full S&P subshells. Oops, drop the pen there. So instead of writing out all the electron configurations, I can just get 8 valence electrons. Or, actually, what I should do is I should write it this way. So here's 8 valence electrons, or 0 valence electrons. Yeah, the cats are rebelling. So yesterday, Steve came over. Steve teaches Chem 161 and 162 and other classes at the college. But we're really good friends. And it's the first time we actually have seen each other in person in like a year and a half. So Steve came over, we played Civ 6 because we love Civilization. And all the cats were just crazy about Steve. Like, oh my god, it's another person that isn't Professor Wes. Like, holy shit, this is the best day ever. We want to see other people. And now they're back with me, and it's just me, and they can't stand it. So, all right. So we already know how ionic bonds form. Ionic bonds form by making ions, and we're going to transfer electrons around until we have full S&P subshells. We'll add that here. And we said this at the end of chapter 3. But now what we're going to do is we're just going to simplify that and say 8 valence electrons are what are needed. The cats refer to me as Professor Wes. Everyone refers to me as Professor Wes. Right? Don't you? It's right there in orange. See, I could see it. No, that's not true. Nobody calls me that. So our goal when we do this is to get to 8 valence electrons on each ion to form our ionic compounds. And so we can do that actually really easily by just drawing pictures. So I'm going to draw the first. Actually, what I'm going to do is I'm going to do this one right here, just since it's a good example here. No, they can't see the bottom of their food bowl. I literally just filled it. So let's show how we can use this dot method here to figure out ionic compounds. Now, this is going to look a lot like a football sort of diagram where I'm just moving dots around with arrows. And that's sort of the point. So for instance, if I want to get everything to have an octet, I need to give chlorine an extra electron. It's got to go here. So I'm going to take this electron, and I'm going to put it here. And if I do that, this chlorine has 8 valence electrons. It has a full S&P subshell. It would not accept or lose any more electrons. It is stable. But I would also need to get rid of this electron and move it somewhere else. So in order to do that, well, I'll just find another chlorine, because there's always more chlorine out there for me to pawn this electron off onto. There we go. So now this has an octet, this has an octet. We can then look at the charges that would form for it. I would get this. I would have these. The total charge balances out to be 0. This is the formula that we get. Now, we've done this already. We have already learned how to predict what ionic compounds form. But what's happening here is that you can now use the Lewis structure to predict that instead of electron configurations. And that gets a little bit easier. You don't have to write out the electron configuration every time once you can just draw the Lewis dot structures for all of your atoms. And that's good. I'm going to have you do a bunch of these examples here so that you can practice it. I'm going to have you do the remaining ones. But when you shuffle electrons around, you're always going to end up with getting 8 on everything or 0. Because remember that if I have... So if I write out the electron configuration for magnesium 2+, so here's magnesium, right? If I remove these 2 electrons, now this is my valence, and I have 8. So if you ever have 0 electrons, then you technically have an octet, or 8. So draw out all of these not electron configurations, all of these Lewis structures for each pair. So do these, try and move electrons back and forth, and see what you can do to get everything to have 8 valence electrons, and when you do that, what's left must be the formula. I'll give you like 5 minutes to play around with that, and then we'll go over a few answers together, and then we'll keep going. All right, one more minute. We'll go over the answers. All right, so let's play around with these a little bit. So these first few are really trivial because the dot that we're moving... Oops, I gotta move the pad up onto the tablet here. The dot that we're moving just fills in whatever gap we need to, and then the problem is solved. So, for example, for potassium, I need one additional electron on bromine, and I just take potassiums and give it right over. And I get that as my result, so that KBr is the substance that we were looking for. And same thing with calcium oxide. So calcium has 2 valence electrons. Oxygen has 6, and it needs 2. So, hey, I'll take your 2 electrons. There you go, sir. There you go. And we'll put all these dots on oxygen. There we go. CaO. Now, for the other ones, I'm going to need more space here, so I got to hit clear. For the other ones, we're going to need multiples to get to the octet. So here, I need to pass 1 electron over, so this sodium is fine. But I need to do that 2 more times for nitrogen. So we'll just take this one and give it over. We'll take this one and give it over. Now everything is good. Now I've done that, I have 3 of these. Na 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 na. Sodium. I mean Batman or whatever, right? And then for nitrogen, I would have that. So my formula is this, not NaN3, like I always want to write for some reason. Somebody found a mistake on the slides, or not the slides, but the lecture. I wrote NaN3 instead of Na3N. So if you see me write NaN3, look in the comments and see if I didn't accidentally mean to write this. And then for aluminum and oxygen, we're just going to shuffle dots around like crazy. So I'm going to take this and move it over here, this, move it over here. This oxygen is good. But I still have an extra dot. I need to get another oxygen. So I'm going to pass that over. Now this aluminum is good, but I still need an extra dot on my oxygen, so we'll just do this again. So now that's good. That's good. And that's good. So there's my compound. There's my ions. You can see that the charges all balance out. There's the compound we make. So Oh, you can hardly see that because I had to scroll down. There we go. Sorry about that. So you can see that we can use this graphical method instead of doing the analytical work of write out the electron configuration, calculate the number of valence electrons, how do I shuffle them around, and sometimes pictures are just easier. In fact, that's going to be sort of the whole point, is that we're going to use pictures to draw bonds between anything that we want to, particularly for covalent compounds, because when we have electrons being shuffled about to make covalent bonds and shared, we can represent that in a really nice way. For instance, with these two elements here, if I take two fluorine atoms and I shove them together like this, I can use this strategy to say, oh, well, everything now has an octet. And we can explain covalent bonding effectively this way. Because you can see right here, oh, there's 8 electrons, but if I go on this side, oh, there's 8 electrons there too. 8 electrons, again, is the magic number for a full S and P subshell. Now, how the heck do I get to put the electron in both atoms at the same time? Well, the electron is accessible to both atoms at the same time, because it's in between them. So if I was drawing my 2s orbital by drawing a circle like that, you could see that the circles overlap, and my shared electrons would be in that overlapping region. We're going to talk about that a little bit more in Chapter 5, how orbitals overlap and how bonds form from a physical standpoint. Now, whenever we draw 2 electrons that are shared between them, we're going to replace that with a line. So if I had something like this, these are my electrons that are shared. Anytime you share electrons in a covalent bond, we're going to redraw them as a line. So right here, this line right in the middle of these 2 fluorines, this is a covalent single bond, and a single bond represents 2 shared electrons. All of the other dots on the outside, they just hang out. And it didn't indicate that. That's okay. So these right here, and any other pair I could have selected, these are called non-bonding electrons. In your Lewis structure, we're going to have non-bonding electrons show up all the time. It's very important to draw them, though. Now, as you've noticed, and I've been repeating over and over and over, every time we do bonding, whether it's ionic or covalent, the end result is that we get a specific number of electrons, 8 valence electrons. And that's because, again, if I want to fill an sp subshell, I need 8 valence electrons. And so this is called the octet rule. You may have heard the octet rule if you've taken chemistry before. You've definitely heard it if you took Chem 140 with anyone here at EVCC. Main group atoms, so these are labeled as 1 through 8A. We're going to use this numbering scheme the best of our ability. 1 and 2, or 13 through 18. These elements form enough bonds, either ionic or covalent, and either abandon electrons, collect electrons, or share electrons, depending, again, ionic or covalent. so that they end up with a total of 8 valence electrons. So again, our goal is to get 8 dots around everything. Lines count as 2 dots. So let's do an example for CF4 and water here. And we're going to show that we can do this sort of connect the dots strategy so that we can make a structure that represents what we see. All right, so we'll draw a carbon, and I'm going to draw some fluorines here. And you know what I'm going to just do? I'm going to do this. Behold the power of computers. Boop. 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 There we go. Let me just merge all those. All right, so now what can I do to share electrons? Now, if I'm going to share electrons, they have to be unpaired. So only unpaired only the unpaired electrons can form bonds. And the reason for that is because in order to form a bond, I would need to share electrons, and at most I can only put 2 on a side. If I shared a pair of electrons, I already hit 2, and I can't accept any more. So only the unpaired ones have the capacity for sharing. The other sides don't need to share. So what that means is that if I'm going to form a bond, it would be between any 2 unpaireds, like that. Or maybe like that. Or maybe like that. And so on. So now we have this sort of connect the dot situation where I can just go, okay, well, this is now connected to this fluorine. And this is connected to this fluorine. And this is now connected to this fluorine. And now you can see sort of how the basics of drawing a Lewis structure come together. Now, this strategy is extremely simplified. And where it tends to fall apart is if we get molecules that are really, really big. But for things like these 2 molecules here, so for water, here are the pieces that we have to work with. And so obviously there aren't that many options here. But you can see how we get the structures out of them. So by doing this connect the dots strategy, you should be able to get a very simple basic Lewis structure. So let's have you do that for a few of these. Now, before I do that really quickly, remember that hydrogen is tiny. Hydrogen is only a proton and an electron, so at most, hydrogen wants only 2 electrons so that it can look like helium. And so we call that the duet rule. The duet rule only applies to hydrogen and helium, and to some extent like lithium. Everything else follows the octet rule. Just hydrogen's the exception. I thought I had some examples for you to draw here. Let me check real quick. I guess I took those out because we're going to go straight to just like the big, here's how to draw a Lewis structure for any molecule. So for something like HCN, yeah, you would have exactly that. In fact, I think I make you draw HCN later. But you'd have a single bond to hydrogen and a triple bond to nitrogen. But yeah, that's exactly right. Now, we can do multiple bonds to different atoms if we want to. So you suggested a triple bond. We're going to show how that works. How that works. Sorry, I said that too many times. So if I wanted to draw the Lewis structure for oxygen, first I could just do this. And then I could say, well, okay, I can pair these two together. That would make a pair. But I could also pair these two. Oops, I messed up. But I could also pair these two together right here. And then once I've done that, I get a frog. Ribbit. No. I get O2, which then rearranges like this. Now, instead of drawing 4 dots in the middle, so there's 4 electrons shared, I could instead write that as a double bond. Because each line represents 2, right? So we'll do that. Now, you could do this with nitrogen as well. So let's draw this for nitrogen here. And I could match those two together and these two together and these two together. And the end result that I get is that. So a triple bond is totally possible. I could share 3 electrons with another atom that also needs 3 electrons. However, 3 is the maximum number that we can share with an individual atom. The 4th electron, for example, if I try to do this with carbon, the 4th electron is not oriented in a direction where I can make my bond occur. So I cannot make a bond that loops around like that. And the reason for that is charge goes in straight lines, right? There's already a nucleus between my 2 electrons, and the electrons are on the wrong sides of the atom. So these bonds actually have to end up going to other things. So the maximum number of bonds that you can make between any 2 atoms is 3 for the purposes of this class. And we're going to show that in more detail later in chapter 4 and then again in chapter 5. Now, the possibility of multiple bonds makes our connect the dots idea rather cumbersome. So if I'm going back to, say, this diagram, and I say, okay, I want you to do this strategy, but what I want you to do it for is carbonate. So I'll fill in my dots, and then this 2 minus means I have 2 extra dots here. And I say, okay, go ahead and connect all the things. And the first problem that you'll run into is like, well, wait a second, I'm going to end up with a leftover electron. And then what the heck do I do with these? And so you end up just in a nightmare of trying to connect everything back and forth. And it gets really, 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 really confusing trying to do this connect the dots method. So what we're going to do is we're going to not use the connect the dots method for anything that isn't a really simple molecule. So like water is fine, CO2 is probably fine, but we're going to devise a new method that will help us work for any molecule that we have. And so that's what we're going to do here. Does C2 specifically exist? So C2 does not exist. This, however, does exist. Why are we mentioning Rule 34 in my chat? We're talking about Lewis structures. I mean, whatever gets you interested in the subject, right? I don't care. I don't judge. All right, so here's how we're going to draw the Lewis structure for anything. Since all of our bonding involves valence electrons, the first step that we should do is to figure out how many valence electrons there are. So we're going to count the number of valence electrons in our molecule. And that's not hard to do. If I know the number of valence electrons an atom gives me, then I should be able to count the number of valence electrons a molecule gives me by just summing them all together. Now, if I have anions or cations, i.e., when I showed you carbonate, I can adjust the number of electrons for that. So if I have an anion, I can add extra electrons, and if I have a cation, I can subtract electrons. We're going to do an example of all of these steps in just a second, but I am going to go through all of the steps first. Once you've counted all of your electrons, the next step is to draw a sort of skeleton. So this is a rough sketch of what your molecule looks like. It is the most basic framework with one bond connecting all of the atoms together. In the molecules that we're going to be working with in this class, some atom goes in the middle, and all of the atoms are bonded to it. Formulas tend to be written to give you a hint as to what goes in the middle. The first element that is not H is the central atom. So, for example, in CO3 2-, C is the central atom. In HCN, C is the central atom. H can never be the central atom. So how does carbon bond together into hexagons? So that is actually a structure that I'm going to have you try and do in a little bit. And it involves alternating single and double bonds. And you'll see how that works in just a bit. But for step 2, draw your framework, connect all your things together. Remember that your connections use electrons. All of your remaining electrons are going to go to just filling octets on other things. So once everything's connected, the next step is to use electrons on external atoms to give them octets, and then give any remaining electrons to the central atom. Step 5 is sort of a check at the end. Make sure everything has octets. If not, you need to make multiple bonds. And those are the 5 steps. So what we're going to do is I'm going to go back to this. We're going to put this on the board here. And we're going to draw the Lewis structure for CO2, which is what the slides are doing in a second here, but that's okay. And I'm going to write a brief summary of the rules on the right here, and we're going to follow these one at a time. So, for example, we're going to look at CO2. We're going to count its valence electrons. So each carbon gives you 4. Each oxygen gives you 6, and there are 2 of them. And so I would add these together, and I have this many valence electrons to play with. Remember that we're counting the number of valence electrons from the electron configurations, which we no longer are writing out because we're just using the group number. Carbon's in group 14. The one digit of that group is 4, so it has 4 valence electrons. Oxygen is in group 16. The one digit is 6. It has 6 valence electrons. All right, so that's step 1. We've done that. Step 2 is to draw our framework. This is the central atom, the carbon here. So I'm going to write it in the center, and I'm going to just put the oxygens around the side here. Let me put that one a little further away. There we go. Now, in order to make it a framework, I got to bond them together. So I'm going to do this. And I'm going to deduct the electrons that I used. I drew 2 lines. Each line is 2. So I'm going to deduct 4 electrons. I now have 12 left. Step 3 is do octets on the outside atoms first. And I'm just going to put dots down until there are 8. So 1, 2, 3, 4, 5, 6. And then the line counts as 8. So this atom has an octet. However, that did use 6 electrons to do that. So I only have 6 left. I'm going to do the remaining 6 over here. And I'm all out of electrons. So I've used them all now. Step 4 is inner octets. However, there are no electrons left for us to put on carbon. So we just move on to step 5, which is multiple bonds. Now, I only make multiple bonds if I have to. If I don't have an octet on the central atom, then I must make multiple bonds. Oh, excuse me. That's the only circumstance that you need to make multiple bonds. Is there an octet on the central atom? If the answer is no, you make multiple bonds. So I only have 4 electrons here, so I need 4 more shared with it. So I'm going to take 2 from this carbon, or 2 from that oxygen on the left and bond them to the carbon. I'm going to take 2 from this one and do that. And now everything has an octet, because this oxygen still has an octet. There are 1, 2, 3, 4 electrons, and then each bond counts as 2, right? So that's an octet. Each bond again counts as 2 for carbon. And for oxygen, 1, 2, 3, 4, bond, 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 bond. So there is an octet around every atom. My structure is now complete, and we can tidy it up. And there you go. So that's the 5-step plan. Count electrons that we can use for bonding, so count up all your valence electrons. Write out the framework, make the basic connections, put all the electrons on outer elements first, put any remaining electrons on the inner atom, and then finally make multiple bonds if you have to. Now, very important things to note about this 5-step plan. You have to do the steps in order. If you skip any steps, then what ends up happening is you get the wrong result. You're also not allowed to backtrack. So if you cannot do a step because you have no electrons, you skip it and go on. So if you run out of electrons on step 3, you stop wherever you ran out, you go to step 4, you've probably skipped that too, and then you go to step 5. And then the final hint that I give is if all of your atoms have octets at any point during this process, stop. your structure is correct. You do not need to do any remaining steps because you probably have no more electrons anyway. All right, so what I want you to do, this is just my walkthrough for CO2, and so you could follow this along on your own if you'd like to just read over it. Let's do an, oh shit, hold on, sorry. I'm sitting here tapping through this and you can't see it. There we go. So this is just like a walkthrough for CO2, and you can see that I'm putting stuff down like we did on the example. So if this helps you, you can pause the video and review it later. So now let's do this for ammonia. So for ammonia here, nitrogen gives me 5 electrons. Hydrogen gives me 1, but I have 3 hydrogens. So I'm going to have a total of 8 electrons. So now I'm going to draw the blueprint, or my framework here. I'm going to just put the H's sort of around it so that I have equal access to all of them. And I'm going to connect them all. 1, 2, 3. 3 bonds is 6 electrons. So I'm going to remove 6 electrons from my total to get only 2 left. Now, step 3 would be to put electrons on outer atoms, but hydrogen only needs 2 electrons, so all the hydrogens are good. So we move on to step 4, put the electrons on the central atom, so that's where we'll put them. I'm out of electrons. Everything has an octet. This is the correct structure. And so we can match that with what I get when I hit the spacebar, and it looks pretty good. All right, so what I want you to do, and you'll have to do this tonight as practice, is I want you to try drawing these Lewis structures on your own time, sort of as like a homework exercise, I guess. Although you have quizzes in a lab to finish, so if you don't do it, whatever, right? Tomorrow we're going to go over the answers when we have time at the start of the class, and we'll show the Lewis structure for all of these things. Don't worry if it seems like you have multiple possibilities, because in the next sections we're going to talk about that. Because the octet rule is a guideline, and we're going to find that there are a bunch of exceptions. And we're going to see all sorts of different molecules as we continue exploring this. But that's all the time that we have today. So when we come back tomorrow, we will continue our discussion of Lewis structures. And we're going to talk about all sorts of different exceptions, as well as different circumstances where we get interesting and weird results. And just try and do the best that we can to make the model match what we observe in reality. I want to thank everyone for coming out to the lecture. Make sure that you get the quiz in for Chapter 3. Make sure you get the lab worksheet in for number 4. Soft deadlines tonight. Last call for those will go out tomorrow. And I'll see you tomorrow for the next lecture. Take care and have a good rest of your day. Enjoy the sun.